My name is Dan Sherson. I'm the president of the Electrochemical Society, and I would like to welcome everyone to the 5th ECS Electrochemical Energy Summit. We are very proud of how what started in Boston in 2011 has grown to become a meeting of this magnitude. The research that you are doing directly addresses some of the major issues people are facing around the world. And our work is about the sustainability of the planet. I want to thank my co-organizers, Krishnan Rajeshwar and Adam Weber, for assisting in putting together this entire program that will focus on solar critical issues and renewable energy. We are excited to have some of the key players in the fields as our 7 key participants. Harry Atwater from the Artificial Photosynthesis Center, George Crabtree from the Joint Center for Energy Storage Research, David Wosolowski from the Fluid Interface Reactions, Structures and Transport, EFRC, Stanley Whittingham from the Northeast Center for Chemical Energy Storage, Gary Rubloff from the NIST Energy Frontier Research Center, Esther Takeuchi from the Center for Mesoscale Transport Properties, and Paul Fenter from the Center of Electrochemical Energy Science. So thank you all for being here. We're also very fortunate to have Franklin Orr this morning as our plenary speaker. As Undersecretary, Dr. Orr is the principal advisor to the Secretary and Deputy Secretary on Clean Energy Technologies and Science and Energy Research Initiatives. Dr. Orr is the inaugural Undersecretary for the office, which was created by Secretary of Energy Ernest Moniz to closely integrate various activities of DOE in the basic and applied research, technology development and deployment efforts. The number of tasks that Dr. Orr is responsible for is quite numerous, so I'll just only give you a little bit of what it entails. He is in charge of the Office of Electricity Delivery and Energy Reliability, Energy Efficiency and Renewable Energy, Fossil Energy, Nuclear Energy, and various others that you can look up on the website. Prior to joining the Department of Energy, Dr. Orr was the Kaylin and Carlton Beall Professor Emeritus in the Department of Energy Resources Engineering at Stanford University, which he joined in 1985. He has since held many positions at Stanford. By the way, he got his PhD from University of Minnesota in chemical engineering. Dr. Orr is also a member of the National Academy of Engineering. He served as a member of the Board of Directors of the Monterey Bay Aquarium Research Institute. He also was a member of the Board of Trustees of the David and Lucille Packard Foundation, and he has served as a member of the National Research Council Committee on America's Energy Future. So with that, I'm very pleased to introduce to you Dr. Orr. Please.
Thanks, Dan, for that introduction. It is a pleasure to be here. It's good to see all of you who are here at this early hour. If we could have the slides, and the clicker seems to, there it is. I don't seem to have control over a... How many PhDs does it take to... Right. Thank you very much. It's good to be here. Good to see everybody. Thanks for the introduction, and thanks for being here early in the morning. So my job over the next little while is to try to give you some sense of something we've been up to at the Department of Energy recently, something called the Quadrennial Technology Review. And so I'll try to put that in context for you here. We've actually released a couple of big reports this year. One is called the Quadrennial Energy Review. It was focused on the energy infrastructure of the country, things like the grid, pipelines, transportation systems that supply all those energy services that all of us take for granted. And it's full of policy recommendations about how to modernize that infrastructure and make it more secure. The second part is what I'm going to talk about today. It's the Quadrennial Technology Review. The first one of these was done in 2011 at the request of the President's Council of Advisors on Science and Technology. It focused on 17 technology areas where there were real opportunities for advancing energy research. This one, 4 years later, so the quadrennial part's on schedule anyway, is aimed much more broadly. It tries to be comprehensive, to look across the energy technology landscape and consider where things stand now and where the opportunities for doing better are in the future. And so I'll try to just give you an overview sense of that today. But I'm going to send you off to our website for the details, because there's an awful lot that is there that is too much to cover in one short talk. So it's actually interesting to think back on where we were at the time the previous Quadrennial Technology Review was done. So that was kind of in the 2010 timeframe. And Dan mentioned the fact that I served on the group that the National Research Council study called America's Energy Future. Doing that sort of thing, Lynn, teaches you humility, because, of course, we tried to foresee what might happen next in the next few years, and I would say some of the things we got right, but we certainly missed on some of the things. One of those was the shale gas revolution and all the additional oil and gas production that came from really a technology advance that involved the ability to drill long-reach horizontal wells and then fracture them to recover hydrocarbons that were there, so we didn't get that right. But nevertheless, that's not the only change in the last 4 years. For those of us who spend our lives trying to think about all this and saying to people that, gosh, the scale of the energy systems, they're so large that it's hard to change them overnight. And, you know, that's still true, but nevertheless, there have been remarkable changes over the last few years. Vehicle gas mileage changes are starting to take effect. That's at least flattened demand for gasoline and diesel fuel, and threatens to bring those down in the future. China, of course, was growing fast and still growing fast by most standards, but not at quite the same pace. So the combination of judgments about future demand there and reduced fuel usage here have caused a big decrease in the price of oil. There are now 5 nuclear power plants under construction in various stages in the United States for the first time in decades. Wind has increased 65% in the last 4 years, solar by a factor of 9 in power generation. Electricity consumption's been about flat as efficiency measures have started to take hold. And so on and on. You really can say that things are changing, and I think we will all look back on this period as one where there really has been a very sharp increase in the rate at which we make a significant transition in the energy mix for this country and then I hope for the world. So you say, okay, fine. What do we want out of an energy system? Lots of people have said versions of this, so there's nothing new here except to say that we're really looking for economic security. That is, a cost-efficient energy system for us is a key underpinning of the U.S. economy. Energy security in the sense that having a diversified portfolio of primary energy resources And the ways we transform those into energy services gives us better ability to respond to disruptions when they occur and to recover when we have to do that. And then, of course, a very important driver now, more important now even than it was 4 years ago, is the environmental security side. Much lower greenhouse gas emissions are an essential feature of going forward. And, of course, that's not the only way we interact with Earth's global systems that we count on for all kinds of services there as well. So, but particularly greenhouse gas emissions and climate change is a primary driver now. But there's also this huge opportunity. At the same time, we can create and manage linked complex systems that deal with all these three challenges. So let's think about how to do that. Now, I will say here at the outset that any kind of snapshot like this quadrennial technology review is exactly that. It's a snapshot. Our view of what's likely to happen tends to be more conditioned by the current state of what costs what and how it compares to others. But we should remember that, that there are learning curves that apply basically to all energy technologies. As we deploy them and as a lot of smart engineers work on making things cost less to manufacture and cost less to operate and more efficient as energy conversion devices, that changes the mix, and they don't all change at the same rate. So, of course, there's an interesting competitive environment in which all of this will take place. My favorite example of this is the engine, broadly construed. So the steam engine was invented in, call it 1700. The first version was 0.5% efficient. So you say, well, that's not very good. But at the time, it was pretty good because it allowed you to build a fire and convert that into mechanical work. And of course, that truly did change the world through the Industrial Revolution. Now, if you fast forward to today, if you use, say, a solid oxide fuel cell with a heat recovery turbine downstream, you can get north of 75% of the energy out of that was in there in the fuel into some kind of an energy service. So that's a quite substantial improvement in efficiency. It did take 300 years, so it would be good to pick up the pace some, but nevertheless, it's evidence of what can be accomplished if we put our minds to it. So, okay, enough introduction. Now, all of you have seen this diagram from our Lawrence Livermore folks many times, and I know you can't read it, but I put it there just to remind us that on the left side there are primary energy resources. Some are stored, like the nuclear and fossil, and some are flows of energy like the sun and wind. But nevertheless, they're all primary resources that we can put to work. And you see right away, of course, that fundamentally petroleum goes to fuels largely for transportation, and all the rest of them pretty much contribute to electric power generation. On the right side are all of us consumers. There's residential and commercial uses, industrial uses, and transportation, of course. So we've used that to kind of organize how this report is written. On the left side, the electricity and fuels take care of primary energy resources directly. On the right side are all the uses. The building icon and the manufacturing icon and the road icon tell you about some of those uses. And the connective tissue in here is the grid. You can't, if you think about trying to operate a modern energy system, it cannot be done without the availability of electric power for all kinds of services. So you say, okay, that's fine. We'll use that to talk about all of this. Now, I'm going to give you very brief sort of highlights of some of these areas, not all of them. I'll just say you should be willing to go look at our website. It'll be on the last slide, but it's energy.gov/QTR. The full report is there, and it will also give you links to 59 individual technology assessments. And I should say right here and now that I'm sure that many of you in the audience contributed to this. There were a couple of hundred of DOE folks, either at the national labs or at headquarters, and about 500 external reviewers who helped us with all of this. So the good news is that I didn't just all make this up myself. There were a whole lot of people. I'm just the spokesperson here today. But there are detailed assessments in the electric generation chapter. For example, there are 19 separate ways that are looked at to turn an energy resource into services. So let me just say a few words about the grid and how it plays a role. I think you can already look back and say that we have been steadily electrifying the planet and our use of energy for something like, many decades now. So that by itself tells you something about the flexibility. In an audience like this, I can actually use the exergy word. So electricity is, of course, has very high exergy, very high availability, so you can do all kinds of things with it. Now, there's typically a big thermodynamic hit as we get from that primary energy resource into electricity, so there's things to work on there. But nevertheless, the ability to supply electricity cleanly at low cost and distribute it effectively is essential to every modern society. So we're kind of in the midst of a transition here as well. So if you think back to I'm remembering my first visit to the Cal Independent System Operator. This would be in the sort of early 2000s. At that time, it took about a second. They had a modest number of sensors around. It took about a second to gather the data and 3 seconds to compute the state. And then so 4 seconds later, you could think about what changes might happen, and maybe a cycle or two would happen there. So the time scale for adjustments was in the tens of seconds. And but it's crystal clear now that there are things that go on the grid that go at much faster timescales than that. So that's kind of the equivalent of speeding down the freeway at 60 miles an hour with your eyes closed about 3/4 of the time. So surely we can do better. Well, along came the global recession, and the federal government made the decision that they would invest funds in a series of so-called shovel-ready projects that would allow basically to pump money into the economy. One of those was to install phasor measurement units around the grid. These just give you voltage and frequency and phase angle. And that set of sensors, if your eyes are good, you can see all those little dots around the United States. Those dots are phasor measurement unit installation positions, and the red lines are where those are gathered into central bits of evidence. So this has actually greatly improved our ability to see what's going on in the grid. And had we had this system in place when the 2003 blackout came along, they would have detected it early enough to do something about it early on. So right then, if you think about the cost of those kinds of major disruptions, they are huge. So this investment will help us do that. So it's a step along the way, but there's a whole lot more that we can do. So let's just think about that for a moment. So the old system was centralized generation. There are thousands, maybe order of 20,000 generating units around the country now, and with distributed generation, that will grow. So this transmission system is better off now than it was, but there's also the possibility, of course, that we'll have lots of generation distributed out on the distribution side of the system. And plus, we have all these smart meters that are out there, so there's information to be gleaned from all of that. In the places that are using the smart meters the best, for example, they no longer have to send that truck out there to drive along the feeder line with the flashlight shining up to see where the tree fell on the line. They can tell by what smart meters are not reporting back in. Now, this does require a communication system that's that's robust, and that you can look at all that data quickly and use it. But even the systems that are using this now have reduced so-called truck rolls quite dramatically and improved the time to get things back on track. So there's really quite a lot that can be done here in terms of using sensors, using active controls on where the power goes, thinking about solid-state transformers, a big limitation on on the availability of transformers. They're basically, all the big ones are manufactured overseas now. With wide bandgap semiconductors and other possibilities, we have the possibility of really changing that business, and I think we should lead the world in that. So now, of course, this comes at some price. I mean, it certainly comes at a price of building and installing the equipment, but it also depends on a secure communications network that goes with this. So the cybersecurity side is important too. Those of us who work for the federal government and now have all our personal information stored in China, actually I don't have any direct personal knowledge that it's in China. It's stored somewhere else on the planet. Just have been reminded that we should be careful with all of this, and so the cybersecurity and the physical security side is actually quite important. But what can come of this is better services, better stability, better operations for our energy future. So we should do that. I'm sure that many people in this room have also seen this famous duck curve. This is California on March 31st, I think 2013, but I'm actually not certain about that. But in any case, you can see these curves. This is a daily generation load curve. And you know, at nighttime, there's a kind of generation. In the daytime, of course, the sun comes up. And there's lots of solar power on the California grid, and once you get down to those curves below the 2013 one, those are all guesses of what it might look like going forward, given the California Renewable Portfolio Standards. And you can see that really the solar is providing a quite substantial fraction of the power in the daytime, but as the sun gets low on the horizon, of course, then there's a quite steep ramp up, so 13,000 megawatts in about 3 hours. So that will need to be accommodated in a way that's different from the way we deal with all of this now. And it just makes the point that integrating big quantities of distributed generation, either at the building level or at other intermediate levels, is also another one of these challenges that we have to deal with. Now, one of the ways, of course, you can do this is with storage. This might be of interest to this particular audience. I see George Crabtree sitting over here. He'll have more to say about this later on in the morning, I'm quite sure, and his will be technically based. I think storage, if you think about any complex system, some sort of capacitance, some sort of storage in the system gives you opportunities to control it in interesting ways. Now, on the transportation side, batteries that might go in a vehicle, of course, it creates the possibility of electrifying a portion of the transportation setting. And that, I think, transportation is hard because those pesky fossil fuels have a very useful attribute, that is high energy densities, you put lots of miles on the vehicle at modest weight, and it's a highly developed technology with a big infrastructure to supply it. So, and it continues to get better, so they'll have to compete there too. But electric vehicles do offer, particularly in the urban settings, some way to reduce carbon emissions, provided we do a good job of the way we generate the electricity. At larger scale, at grid scale, providing some stability when you don't have as much rotating machinery and rotational inertia in the system, that's a possibility there. And of course, there are lots of different timescales for all of this. On the millisecond time scale, maybe supercapacitors are just what we need. On the day-night cycle. It needs to be something bigger. On some time scale, demand response is as good as storage, so being able to shift things. So it's a complicated landscape, and we haven't quite figured out how to value all these services. This is a complicated technology landscape with lots of avenues being investigated. I think that this is one of the most exciting areas out there. Just to pander to this audience, this combination of electrochemistry and nanostructured materials of all sorts and catalysis just gives us such a wide space of opportunity that there really is a huge amount that can be done here, and lots of opportunities to investigate. So storage matters. We need to work on it, but it's also true, I think, that in a grid with all of this going on, we have to understand the regulatory environment and the control environment in a way that we haven't yet done. And that actually brings me to my next point, that you can think of the electric power system as a complex system of systems, maybe right down even at the building level. The electric power market is something like 150 million customers out there now. And so if we're really starting to try to think about this as an integrated system, it's going to demand some computing resources that we haven't yet put to work. It will need fast acting system models and automatic controls and active controls on where power goes. And those are all pieces that need to be invented. It's also a regulatory and market environment that is about as complex as you can imagine. There are 50 public utilities commissions at the state level. There are the regional transmission operators and load balancers, and we haven't quite figured out how to deal with valuation in all those markets. So plenty to do yet, and lots of room for thinking. I said already that if we're going to busily electrify everything, then we will need to generate power cleanly. So let me say a few words about how that goes. On the coal side, I think that there will be fossil fuels of one sort and another in the energy mix, particularly in the electric power generation, for a long time. So one of the options here is to think about capturing and storing the CO2. We already do this at commercial scale now in refining and natural gas processing operations. The scale that we're talking about for electric power generation is bigger by a lot. So this can be one thing that helps, but it can't be the only thing. The issue here is cost. We know we can do it, but it needs to have lower energy costs, and it needs to have lower capital costs and operating costs. There is interesting work going on in separations. Is fundamentally the biggest cost is separating the CO2 from something else. You can do that by separating oxygen from nitrogen at the upstream end, or separating CO2 from nitrogen plus whatever else is there at the downstream end. And even if we really do sharply reduce the total amount of coal in the mix, replacing it with natural gas will require us to do some carbon capture and storage by mid-century anyway, if we're going to keep that in the mix. So, on the nuclear power side, I mentioned that there are some nukes under construction now. These are Gen 3 reactors, the AP1000s. There's research opportunities for high-temperature gas-cooled reactors, for more efficient power generation, fast spectrum reactors, but these are a long way out. The nearest term issue is the idea of small modular reactors. These have the potential, at least, to have no pumps, done thermally with thermal convection, to be much simpler to operate, much smaller, maybe at the 50 megawatt scale, so you could build the thing in a factory, put it on a truck, install it in a place, rather than having the incredibly complex construction systems that we have now. And that they're passively cooled and have enough cooling capacity at the site to operate indefinitely with no electric power and to do a black start. So now, these are just, the first one of these is just approaching design certification, so it will be a while yet. The optimistic pathways say mid-20s for installation of the first ones. Fundamentally, these are all about materials, environments, and simplified designs, so they're still challenging, and we still have to figure out about waste storage and siting and licensing and cost. The primary barrier for nuclear deployment now in the U.S. is cost. Now, let me say a word or two about cross-cutting applications. I said already that there are lots of different potential primary energy resources that get converted to electricity. Almost many of these use a turbine of some sort. And so this is a picture of a conventional turbine on the left side. This is a 300 megawatt steam turbine. It has 2 sides, and there are 5 turbine wheels on each one. On the right side is that little teeny one down at the bottom uses supercritical CO2 in a portion of its pressure temperature space where it's much denser. Supercritical temperatures can't be liquefied, but it can be made dense. And that's the size of a turbine that would be required to generate 300 megawatts. And you say, well, why does this work? Well, it works because any wing, so these turbines are just a collection of wings, the mass flow over that wing that gets deflected determines how much thrust is added to the rotating machinery. And because you're using a denser fluid, it's denser than water vapor, then you can have a smaller turbine. So you say, great, sign me up. Why aren't we doing this? And the answer is, of course, that there are materials challenges to be dealt with, plant integration challenges, and so on. So there is work going underway, but it would apply really across a big wide spectrum of the generation space. It would also allow us to deal with another problem that we have to face, in the sense that the temperature of the stuff that's coming out of the downstream end of the turbine is high enough that dry cooling would be a possibility, that it wouldn't require the condensation using water. 40% of the water withdrawals from rivers and lakes in this country are for thermoelectric power generation. That's bigger than the agricultural withdrawal, although the amount that gets evaporated and consumed is higher in the agricultural setting. So we should remember that water and energy are connected, and there are lots of opportunities there too. It's also true that that's another place where the separation of water from, say, salt water as an archetype, is something that if we could do that more efficiently with less energy required, it could change the planet. And we might need to do that, particularly in California. So in any case, lots of possibilities there. It's interesting what happened. There we go. Of course, wind is up to 4.5% of the electric power generation in the country. It's competitive now in the best resource places without a subsidy. It's the optimistic estimates say that you could get to something like a third of the power if we really used all the capabilities that we had. Optimizations are apparent. There's a question about tax credits and so on, but there really is a big opportunity there. But it also requires that we have a robust grid to distribute it. On the solar side, of course, it's the same situation. Big reductions in module costs over the last 5 years. Still a very big potential. The sun is the really big resource, and there are lots of exciting materials research efforts underway, plus some effort on all the additional costs, the soft costs of installing these things. So lots to think about there. And there's plenty of geothermal and hydro and marine and hydrokinetic potential as well. So let me say just a few things about buildings. 3/4 of the electricity ends up in a building somewhere. might be residential or commercial, which says that we should go after making that absolutely as efficient as we can. If we just applied the Energy Star technologies that are out there now, this is stuff we know how to do. We could knock 20% off our electricity consumption. Now, you might say, well, what the economists always say is that if there are $100 bills lying around on the floor, how come nobody picked them up? And that's an interesting question. It's a behavioral question. I think it's fundamentally about paying attention, that when you, and I know that in my own house when I installed the PV cells, of course that forced me to go look at where the heck all that electricity was going. And when I did, I found ways to reduce it by about a third before the solar cells even got there. So I think that I'm not the only one on the planet to whom that applies. But it does say that we should pay attention to this, and there are many opportunities of ways to do it. In some ways, it's not just one fix for a building. It's windows, it's lighting, it's heating and cooling and ventilation and on and on. But there really is a big opportunity here, and we should be all over it. Largely because these things pay out very quickly, so they are in our economic interest for sure. What about transportation? Well, even the most optimistic of us about transformations here think that combustion will likely continue to play an important role. So we sure as heck should make that as efficient as possible. There's lightweighting, and then there's a whole bunch of electrical stuff. So let me move to that. You know already that the Department of Energy has been engaged in something called EV Everywhere. And this, again, thinks about batteries and electric drive systems and lighter weight structures. And all these possibilities, and it has some goals in terms of costs that I'm pretty sure George Crabtree and colleagues are going to talk about later, so I'll scoot right past that. It's also a place where we've done lots of experimentation at DOE, so all the way from the basic science side with to the Energy Frontiers Research Centers and through work sponsored by Energy Efficiency and Renewable Energy in applications that might go specifically to vehicles, and ARPA-E has worked across this spectrum as well. And the Department of Energy has over the years, it's fun to look back at the history and see that the sort of membrane electrode assembly that we all use in most settings involves a whole bunch of patents that really came out of largely Los Alamos in the early stages. So looking back into ancient history in the 1990s, we actually can see an impact of the work that was done there in the work that's going on today. And of course, you know that the first commercial vehicles that either for leasing or purchase are starting to appear. I had the pleasure of driving the Toyota version of this, the Mirai, when it came to visit DOE in the not too long distant past. The thing that I guess that I came away saying is this, well, you know what, it's a car. It was just like driving any other car. It had lots of zip, and aside from the fact that it was quiet, it really was a pleasure to drive. Cost, of course, is the issue. Hydrogen storage. There are lots of pieces that go into making this fully functional. And let me advertise now for lots of the other speakers that are coming up. There's a seminar to demystify working with the national labs. I'm thinking maybe I should attend that seminar. You know, I could figure out how only 13 of the national labs report to me, or report through organizations to me, but even the other 4 all do some work for us, so it would be good if I understood that better. There's a poster session, there's a collaboration corner, and a booth, and all kidding aside, we really do count on all of you to be able to deliver things so that people like me can stand up here and talk about what you do. So please do stop in and talk. The reason for gathering at places like this is to make all that go forward. So the good news is I'm getting close to the end here, but let me just say a few things about the systems aspects of all of this. You know, one thread that runs through this whole report is to say we should think about making individual technologies efficient. Absolutely. Making each step in a chain of transformations be efficient is an absolutely good thing to do. But there are some opportunities that arise out of thinking about the system as a whole, and we should not neglect those. And in particular, there are plenty of these complex system ideas that can be applied. And one of them is just the manufacturing plant. Manufacturing plants, depending on what they do, of course, can be quite complex environments, and slathering them with sensors and thinking about the process controls and all of the pieces that go into the integration of those gives us some opportunities as well. And then there's the advanced manufacturing side of things. This is a sexy example. Those of us with the gray hair in the audience can remember the Shelby Cobra, this 427 cubic inch rocket that met no safety standards whatsoever. But in any case, in fact, I think it was unsafe to start the engine, you know, and get in the thing. So, but in any case, it was a wonderful car, and we all thought it was the best thing on since sliced bread. This particular, the design here was 3D printed as a prototype. Went from the design drawings to a printed car. The machine to do the printing is down there at the bottom left. It's at Oak Ridge. And it took about 6 weeks. Now, the point there is, one, that you can make complicated bits and pieces by additive manufacturing. And two, it shortens the cycle time for building a part, trying it, and doing it, and so on. So it really is potentially very important. What happened here? So this is an example just of the kind of thing that you can do. So on the right side there, you see a couple of airplane brackets. So they hold something together on a commercial airplane. I don't exactly know what part it is, but and if you do the traditional machining, it takes about 8 times as much material to make the part as you actually get in the part when you're done. If you do the same thing by powdering the metals using what amounts to the kind of technology for inkjet printing to deliver the bits of metal, use electron beam melting to just melt the little bit that you need rather than the whole darn thing, you can end up with a part that has a complex shape. It weighs 0.4 of a kilogram, so a 60-odd% reduction in weight, and the energy use associated with that part flying in the airplane, where weight matters big time, the conventional one uses 3 times as much energy over its lifetime. So that's a case that saves you on the materials side, it saves you on cycle time to try and test this part, and it saves you on energy use. So that's what I mean by the kind of systems aspect of thinking about all this. So I will just say that fundamental to everything I've talked about is the enabling science and computing. So many of you, I am sure, have taken advantage of the services, the scientific capabilities at the 28 DOE national labs, or the user facilities at national labs. And those are an unparalleled, unmatched in the world set of capabilities for the scientific community. And just as a tiny little example, in the middle of, on the right side of that plot there is an image of a turbine blade. That turbine blade was manufactured by additive manufacturing, so that kind of efficient process. And the image was taken with a spallation neutron source right next to it. And it images residual stresses in that turbine blade. Now, all of us who cruise around in airplanes with turbines in them would like those turbine blades to hold together, because otherwise they're shrapnel. And so the ability to create a part like this, demonstrate that it meets specifications and that it will hold up in service, and do that quickly, that's just a huge advantage going forward. It's one tiny example of the kind of thing that we can do much more broadly, using the kinds of resources that we have to make advances in all kinds of directions that will fit together in ways that none of us quite foresee now. There really is huge potential. And equally important to all of this is high-performance computing. We are embarking now on a journey to get to the exascale computer. This is kind of 100 to 1,000 times faster than the existing ones. This is a very big challenge from the software side, from the system architecture side, and from the energy side. If you just scale up conventional parallel processors to this kind of speed, we'd have to have one of those small modular reactors sitting next to each one of these computers. That's probably not okay. So we have to work on all of that as well. So it really is, DOE contributed quite substantially to the revolution in computing that came about when we agreed to stop testing nuclear weapons, and we began to use computing to try to understand the performance and make sure that we met our obligations there. This time around, that was largely led by the weapons side, but immediately adopted by the scientific community when it was available. This time it's an equal partnership between the national security side and the scientific side, so that's important too. So in case you haven't already downloaded and read the 500-page report, or maybe you're not intending to, here's the summary of it in 4 bullets. We've done a lot, but there's a whole heck of a lot more to do. There is a very wide-ranging opportunity space, both for individual technologies and for improved systems, and we need to work very hard across a full, well-stocked portfolio of research. It needs to include a wide range of primary energy resources, conversion technologies, systems and timescales for application, with efficiency everywhere in that whole process. And we need to remember how important to all of this is the fundamental enabling science and computing. So with that, I will stop, and I will be happy to respond to a few questions. And if there's anything hard, I have my DOE colleagues here, and I will pass all this off to them. So great. Thank you all for listening.